Hello and welcome to the Payoff matrix tutorial. You won't need this one probably for the test on Wednesday the next week, but anyways, for the exam and for future semesters, this will be useful. So I have kind of struggled with how to best present this on the computer, and I think I've got something. Anyways, Professor Beauregard is preparing a test for his students at the same time the students are preparing for the test, i.e. studying. Professor Beauregard chooses whether to make the test difficult or easy, and the students choose high or low preparedness, so how much they study. As long as the class chooses high preparedness, so they study hard, Beauregard is indifferent between an easy or difficult test. If the class is unprepared, i.e. they choose low preparedness, Professor B loves nothing more than to punish them with a difficult test. This gives him the highest utility. The worst thing for Professor Beauregard, is if the students choose low preparedness and get away with it because he's made an easy test. The students' preferences, they prefer to be highly prepared for difficult tests and prefer to be unprepared for easy tests because they spend less time studying. The students also always prefer an easy test to a difficult one. Draw the payoff matrix and show any Nash equilibria. So you might want to write this question down if you sort of struggle with these concepts, because I'm going to be referring to the language in the question when I'm doing the answer, but of course it will not be on the screen because I'll be in Journal doing the answer. So go ahead and pause it, try to come up with this payoff matrix. I don't really care whether you assign letters and give me a ranking or just put in numbers. As long as the numbers agree with the ranking that I give you, and I will give you a sample number thing to work with also when we get to the part where I do the solutions. And don't forget about the Nash Equilibria and how they should be written. Okay, so we've got two players. We've got the professor, and his choices are difficult or easy. And we have the students, and they can choose high or low preparedness. So let me just draw in some lovely little boxes here so that it looks like what you're used to. Again, I apologize for the unprettiness of this, but it'll get the job done. Okay, so the first thing that I said in the question was as long as the class chooses high preparedness, the prof is indifferent between an easy and a hard test. Okay, so we know that the player who is on the top is represented with the second number in the sequence of numbers. So we're going to give him A for difficult with high preparedness and A for easy with high preparedness, right? Because he has to be indifferent. These have to be the same number. Okay? The other thing I said was that if the students are low preparedness, the very best thing to do is to punish them with a difficult test. So that's going to be B. And then the worst thing is if they're low prepared and he gives them an easy test. So that's going to be C. Okay, so based on what I said, if the very best thing is, and it really gives him pleasure to really screw you when you don't prepare well for a test and make a super difficult test, then B must be greater than A. Okay, so if the favorite thing is to be a real bastard and give you a hard test when you're unprepared, then B has to be greater than A. Okay. If it's also the case that it's good to be evil and make a really hard test when you're unprepared, then B must also be greater than C, right? So if B is the best, then B has to be greater than both A and C. Okay? And I also said that the worst thing was that he lets them get away with being unprepared by making an easy test. So A must also be greater than C. Okay? And by the transitive property, then I can come up with a ranking here where B strictly preferred to A is strictly preferred to C. Okay? And that's how I want to come up with payoffs. Okay? Now for the students. Okay? The students regardless of preparedness, prefer an easy test to a difficult one, and they prefer to have prepared for a hard test and be unprepared for an easy test. Okay, so it looks to me like we've got probably the case for four different things here, right? Because there's nothing where I've said that they're indifferent. So I'm going to call this D, I'm going to call this E, I'm going to call this F, and I'm going to call this G. Okay, so we've got four different payoffs here. Okay, so the first thing I said was that a student always prefers an easy test to a difficult test. So D must be less good than E, and D must be less good than G. Okay, because those are both easy tests, and they have to be worse than, or have to be strictly better than a difficult test. So by the same logic, F has to be worse than E, and F has to be worse than G. Okay, so that's my first thing that I've said. Okay, so they also prefer to be prepared for a difficult test. Okay, so if test is difficult, being prepared must be better than being unprepared. So D is better than F. Okay, and they also prefer to be unprepared for an easy test. So G must be better than E. Okay, so I can already see by sort of these first four things that G and E are preferred to F and D. Okay, so they have to be at the top of the ranking order. And I have here that because they prefer being unprepared for an easy test, that G must be greater than E. So the first two in my sequence must be G is better than E. Okay? Now I have to have some ranking in between D and F, and of course, because they prefer to be prepared for a difficult test, then D must be greater than F, and I have here that E must be greater than D. So I've come up with a ranking system for the other payoffs. Okay? So with this information, and I'm going to get rid of these boxes around this other stuff because I just went box crazy here for some reason. I do want a box around this, but not really around the rest of it. Okay, so those are my two series, and it says nothing about what B is relative to G because it doesn't, A, it doesn't matter, and B, I didn't give you any information about that. So if I want to, from here, I can set up a Nash equilibrium. I can figure out what it's going to be. Just for the sake of doing more to show you how this works, I'm going to assign numbers to things because I can. So as long as I pick numbers such that B is greater than A is greater than C, and G is greater than E is greater than D is greater than F, then it doesn't matter what I choose. Okay, so I'm just going to go with the easiest possible thing, because 3 is greater than 2 is greater than 1. Then B is going to be 3, A is going to be 2, and C is going to be 1. Okay? And in 2GG3, you'll learn that the actual number assigned to utility really doesn't mean anything because any positive monotonic transformation to a utility function leaves the function unchanged. So if you want to memorize that rule now, you've got a leg up for next year. Okay, so by the same logic, 4 is greater than 3 is greater than 2 is greater than 1. So G is going to equal 4, E is going to equal 3, D is going to equal 2, and F is going to equal 1. Okay, so I'm going to go through and redo this payoff matrix with these numbers that I've assigned. And then I'll show you how to do a Nash equilibrium, hopefully, in a somewhat clear manner. Okay, so my first payoff is D, and I said that D was equal to 2. Okay, I also said that A was equal to 2, so this cell is going to be 2, 2. I said that E was equal to 3, and A is still 2. I said that G was equal to 4, and C is 1, and F was equal to 1, and B was equal to 3. Okay? So I want a Nash equilibrium. And what a Nash equilibrium is where there's no incentive for the other or for the person to deviate, taking the other party's strategy as given. Okay? So what that means is that if I fix someone's action, I'm going to pick the best payoff for the other person, taking that as given, okay? So the first thing I'm going to do is I'm going to fix the student's action and decide what the prof should take, okay? So hopefully with one continuous line, I'm going to cross out low, okay? Because I'm not considering the case of low. So if I fix the student's action at high, then from the professor's perspective, I'm choosing between a payoff of 2 and 2, okay? So I should be indifferent between 2 and 2. So I'm going to put little stars next to both of those payoffs. Okay? Now that gives me the best response, to use the lingo, if students choose high. Okay? Now I'm going to unblock the high cell, or sorry, the low cell, and I'm going to block off the high cell. Okay, so I'm going to find the professor's best action if the students choose low. Okay, so now I'm comparing a payoff of 3 with a difficult test and a payoff of 1 with an easy test. Okay, so here we're not indifferent, and here we're just going to put a star next to 3. Sorry, I keep opening those menus, because that's the best response to students choosing low. Okay, so now I'm going to do the same exercise, only I'm going to take the prof's action as given. Okay, so the first thing I'm going to do is assume that the prof makes an easy exam. Okay, now from the student's perspective, I'm choosing between a payoff of 3 for high preparedness and a payoff of 4 for low preparedness. Okay, well, the students are going to prefer 4 to 3. Okay, so that's going to be their behavior. Okay, now I'm going to fix the prof's action with making a difficult test, and I'm going to block off the easy test column. Okay, so I mean, if you're doing this on a test, just cover it with your hand or whatever helps you figure it out. So now for the students, I'm comparing high preparedness with a payoff of 2 and low preparedness with a payoff of 1. And they're going to choose high preparedness because that gives them the better payoff. Okay, so when I unblock this last column and look at the whole matrix again, okay, I have only one cell where both things are so-called best responses, and it's this cell where I've got a star next to both items. Okay, so that tells me that my Nash equilibrium Nash EQ, for those of you who can't read because that is all one word and it shouldn't be, is, and when we're doing a Nash equilibrium, we write the actions and not the payoffs because, as I mentioned before, the payoffs are arbitrary. So the Nash equilibrium is high, comma, difficult. And I think this is the model that we all have in mind when we make your test difficult. So now you understand why we do what we do. Okay? Because we want you to study the material and learn it. So again, I can do the same thing using these letters, right? Because I've got this ranking system. So I am just going to do that. If you've got the message and you know how to do this and you got the right answer, you might as well pause the video because I'm not going to add anything new here. I'm just going to do the same thing again with the number or with the letter variables instead of the numbers, okay? So again, this time I'm going to start with the professor. I'm going to fix an easy test. So the professor chooses easy, okay? And now the students are choosing in between a payoff of E here and a payoff of G here. Okay, well if I look at my ranking system, I see that G is better than E, so I put a star on G. Okay, now I erase that line. I'm going to fix the professor's behavior as setting a difficult test. So I'm blocking off the easy column. And now for the students, I'm comparing a payoff of D with a payoff of F. And I look at my ranking system and I see that D is strictly better than F. So I'm going to put a little asterisk there. Okay, now for the other side of the matrix, I'm going to fix the students at high preparedness, so I'm going to block off the low preparedness column. And I look at the payoffs from the professor's point of view. I'm comparing a payoff of A with a payoff of A. And of course, those are both best responses because they're the same value. Okay, now I'm going to fix the student's preparedness at low. So I'm going to cross off the high column. And now from the professor's point of view, I'm comparing a payoff of B with a payoff of C. Okay? And B, according to my ranking system, is strictly better than C, so I put an asterisk here. Okay? Now I'm going to unblock all the columns, look at my payoff matrix with all the best responses on it, and again settle on high difficult as a Nash equilibrium because it's the only cell where two elements have our best responses. Okay, now there's plenty of examples of games where there are no mutual best responses. There's no Nash equilibrium in pure strategy, as we say, so you can't just say, well, I'm going to pick something all the time. It turns out that in those cases you want to randomize. So if you think of playing rock, paper, scissors, right, you don't pick rock all the time because the other person's just going to pick paper all the time and you'll always lose. So you randomize in between the three, and if you go into more advanced game theory, you'll learn how to solve those. But for this course, if you can make a payoff matrix and you can figure out what a Nash equilibrium is, just like I just showed you, that's more than sufficient. Well, I guess it's not more than sufficient, that's sufficient. And so it makes sense to learn this stuff.